Hi, we're back, and we've all turned off YouTube, which means if you're going to type any questions or comments, please use Rocket because we don't see the chat on YouTube. Okay, so now we'll start with the first presentation by Jamie Bieron from William and Mary in his paper co-authored with Peter Pierce. And so I believe you'll be able to see Jamie, but we'll start with the recording of his presentation, and afterwards we'll have questions.
Hello everyone, and welcome to our talk in Adaptive Metric for BRDF Appearance Matching. If you have the measured reflectance of a material, then the problem of finding the best parameters for an analytic model so that it best recreates the appearance of the measured material is called BRDF fitting. In our EGSR paper, in Adaptive BRDF Fitting Metric, we will show how to improve the appearance of BRDF fits with an adaptive two-stage algorithm. Our work will be presented on Thursday in the BXDF session. It's the first paper of the day. I hope you will join us for that presentation as well. But what if you don't have the BRDF measurements of a material? Perhaps the only measurements you have access to is a photograph of that material. In that case, you are trying to match the appearance of the material instead of fitting the BRDF data itself. One strategy you might use is inverse rendering to try to solve for the BRDF parameters. For inverse rendering, you need an input photograph to match, accurate scene parameters for lighting and geometry so that the only unknown is the BRDF, and lastly, you need a metric to optimize for. For our input, we will use a rendering of a mural material. This solves the problem of scene parameters, since we are rendering the target image. This way, we can focus strictly on the question of choosing an image metric to use as our cost function. One option would be to use a simple L2 pixel-wise difference, but this does not always give good results. Using a perceptual image metric, the quality of the appearance match improves. In this case, we are using CSSIM. Using CSSIM for inverse rendering gives visually accurate results, but it is slow. Perceptual metrics rely on image structure, so you need to render the entire image at every step. Additionally, they often have poor error landscapes with many local minimas, and they can be hard to differentiate. Here are two more examples of a reference material with an L2 appearance match versus using a perceptual metric, CSSIM in this case. As we can clearly see, the perceptual matches are better. In the case of blue acrylic on the top, the perceptual match is considerably sharper. In the case of gold metallic paint, shown below, the difference is actually more in the diffuse color, best seen around the outside of the sphere and in the lower half away from the specular highlights. I hope this has convinced you that using a perceptual metric has its advantages. In an adaptive BRDF fitting metric, we introduce a novel BRDF metric with a free parameter gamma. For this project, we tested the use of a gamma compression function for use on images instead of BRDF data. Our two-stage approach is analogous to our BRDF fitting work. You can see the metric here as a tone mapping, but without any clamping to 1, and with a variable gamma. Our motivation here is that we want to get results of comparable quality to directly optimizing CSSIM, but at much lower computational cost. We tried reducing the resolution for our inverse rendering scene, as shown here. At half resolution, meaning 1/4 as many pixels, we already start to see some blurring. Note that all of these images are rendered at the same resolution. It's that the BRDF parameters were obtained by inverse rendering at the lower resolution listed. Having the resolution again, we see that the blurring gets even worse. Clearly, this is not a viable strategy. Inspired by our two-stage BRDF fitting work, we were able to get the following result with about 100 times less rendering than the full resolution CSSIM optimization. As mentioned before, we use a two-stage algorithm for BRDF matching. In the first stage, we begin with the HDR image of the target material. Then we use our metric with an inverse rendering system and a range of gamma values to generate a set of potential matches. We then use a renderer to generate images corresponding to those candidates. We then compare each of those images with our input image using a perceptual metric. This gives us perceptual errors for each potential match. We find the candidate match with the lowest perceptual error, and that gives us our final BRDF parameters. We call our method adaptive because as opposed to using a fixed cost function to optimize the BRDF parameters the same way for any material, we use the free parameter in our metric to adapt it to the material being matched. Let's look at some more results. Here we can see two more materials which we want to match. Here are the matches optimizing CSSIM directly. And here are the results from our two-stage system. The loss in quality going from directly optimizing our perceptual metric to using our two-stage approach is minimal. Clearly, the first inverse rendering stage of our algorithm is important, because if we have bad candidate matches, we will have a bad final result. Let's examine the impact of lighting. What if we perform our inverse rendering under the Grace Cathedral probe? How about Uffizi Gallery? Does it need to be natural lighting at all? Our experiments indicate that natural lighting is very important. We tested directional lighting on a sphere, as well as Havren et al.'s specifically designed shape and scene with a point light, and found that even relatively bad natural lighting conditions, such as Grace Cathedral, were much preferable to point or directional lighting when doing inverse rendering for material appearance matching. Even different natural lighting conditions can have a major impact on the quality of the BRDF parameters estimated from a given scene. In the center, we can see the measured material under the eucalyptus grove lighting. Fleming et al. Found this lighting to be particularly good for humans judging material appearance. On the left side, we can see a rendering using the BRDF parameters found by inverse rendering with the L2 metric on a sphere lit by the Grace Cathedral probe. On the right side, the parameters were found using the Uffizi Gallery probe. As you can see, the Grace Cathedral result is badly miscolored. Grace Cathedral's lighting is very colorful, and there is little diffuse lighting. This leads to miscolored BRDF matches when using the L2 metric. Now we can look at the results of our two-stage algorithm. The impact of lighting is still present. The Uffizi Gallery match has blurrier highlights than the Grace Cathedral result, and the Grace Cathedral result's diffuse intensity is not as accurate. Here is red metallic paint, and here are the same four results, L2 and 2 stage, for each of Grace Cathedral and Uffizi Gallery. Next comes gold metallic paint, and here are the four potential matches. Both of these materials follow a relatively similar pattern as the results from aluminum shown at the top. Finally, let's look at blue acrylic. For blue acrylic, note how with the Uffizi probe, which is a very low frequency lighting for a natural scene, you get blurry matches. In this case, Grace Cathedral actually does a bit better. Nevertheless, the adaptive match is not quite so blurry as the L2 match for Uffizi Gallery. We find that optimal gamma varies by material. Therefore, you cannot simply use a single metric for all materials. We have shown that our adaptive two-stage algorithm can outperform L2 and come close to the quality of full-resolution CSSIM, but the astute observer may observe that we have only made things slower. Now, instead of one long inverse rendering procedure, we need to do many, one for each gamma we want to test. And because we find considerable variation in the optimal gammas for different materials, our two-stage approach is not looking like a very good plan. The problem is that we need to render an entire image at each stage of our optimization. We must leverage the pixel-wise nature of our gamma metric to cut down our rendering costs by a large amount. Fortunately, we can. By rendering only a small number of pixels in our scene, we can accelerate our rendering dramatically. However, just choosing pixels at random will not lead to visually good matches. You need to select your pixels carefully. Effectively, you are estimating the error using Monte Carlo integration. We found that we could use far fewer pixels if we used an importance sampling strategy, specifically using pixel intensity as the PDF. Note that it is important to mask out the background when you are selecting pixels. Otherwise, you might end up getting something like this, as I did on my first try. So always remember to mask your target object. We concluded that 256 pixels sampled using our importance sampling strategy was usually sufficient to get quality reconstructions under natural lighting conditions tested, including Grace Cathedral and Uffizi. Here are 6 examples of matches obtained with our two-stage method using all of the pixels in these images. Below, you can see the results when using only 256 pixels for the generation of our candidate matches. It is important to note that while the candidate matches were obtained using only 256 pixels, the selection of the best match from among the candidates is done on the full image. However, since we only test 21 gammas, the cost of selection is constant and trivial compared with the costs of optimizing using the full scene. The overall speedup is proportional to the fraction of pixels we use and inversely proportional to the number of candidate matches. We always use 21 gammas. Our images are 256 by 256 pixels. So our speedup when using only 256 pixels is approximately a factor 10 in total. We found that in many cases, just 32 pixels were sufficient to give good results, especially when using the Eucalyptus Grove light probe. With only 32 pixels, we could see a speedup of over 100 times. The example given earlier of blue acrylic used only 32 pixels, yet it clearly outperformed the lowest resolution CSSIM match, despite being far faster as well. As before, lighting has an impact on the quality of our BRDF matches. Here we have renderings in our Eucalyptus Grove scene for BRDFs obtained from the Grace and Uffizi probes as before. The upper row shows the results of using the full image. The bottom row shows the results when using only 256 pixels to generate the candidate matches. And now for gold metallic paint. Note how that with 256 pixels as opposed to the full image, we see that the L2 match from Grace Cathedral suffers from a similar color distortion as we saw with aluminum. However, our adaptive two-stage process can still find a good match because it sees the entire image in the second stage. For Uffizi Gallery, even though the L2 match has a somewhat sharper specular highlight, note the completely wrong orange glow on the left edge of the sphere. In conclusion, we have shown a method for finding perceptually good BRDF matches with significantly less computational cost than optimizing a perceptual metric directly. Even though it is well known that L2 image matching does not lead to good BRDF matches, we hope that our work might shed a little light on why. The optimal gamma, according to perceptual metrics, varies greatly between materials, meaning that choosing an image comparison metric for material appearance is not trivial. Finally, while we have shown that our two-stage strategy with a variable metric has some effect on appearance matching by inverse rendering, it is much more impactful when fitting BRDF data directly, as we will show on Thursday. We hope that you can join us then, and we are happy to take any questions.
Okay, so thank you very much, Jamie. We all had our YouTube on and off, so not everybody could hear it, but it was a lovely presentation.
Thank you.
And I want to encourage people to enter their questions for the speaker in Rocket in the channel with the hashtag adaptive metric, so that then Jamie and I can see it and we can redirect it. While we wait for everybody to get synced up here. Well, one thing I should say, on YouTube, there is applause. Okay, so just to start off, so in doing this, you did experiments with the Merle database. Mm-hmm. But when you if you create some experimental measurements, say using Cook and RNAR combined BRDF, and you do some synthetic BRDF measurements, when you go through this process, do you exactly recover the parameters that you used to create the synthetic?
So typically, yes. And we didn't do much testing of that in particular, but we did work on trying to fit less advanced models, including Phong, to more advanced models like Cook Torrance and GGX to test that. And so we found that going between analytic models was tended to be a lot smoother of an error landscape than trying to fit to the Merle database. And so going between the same analytic model, I believe we tested, and I recall it pretty much recovering perfectly up to the optimization we were using was not deterministic. And so at the end, it would end up just deciding to cut off when it was pretty close. But we typically find it pretty close, and we found that moving between two analytic models tended to work pretty well.
I mean, it's sort of necessary but not sufficient.
Yeah.
So a question is, I'm curious what algorithm you use for fitting. Also, do you have derivatives to guide the optimization?
So we did not use a differential renderer for this. We did this a few years ago, and it was more of a side project in the context of our fitting to BRDF data that we were doing. And so we used MATLAB's pattern search, which is a just basically test a grid around the point, and then if you find a better direction, move in that direction. And so no derivatives, and I mean, definitely not a fast optimization algorithm, but we found that it needed to be pretty robust in order to deal with things like rendering noise. And even once we used like a fixed seed for the renderer, the error landscapes were pretty bad. So we tended to just use a brute force search of surrounding points.
The next question, you mentioned earlier that SSIM suffers as it requires structured input. What was your new perceptual loss function that does not depend on the pixel structure?
So we were using, actually, if I can share it was in the slides, it's using each pixel individually, we raised the pixel values to 1 over gamma to act as a compression, similar to using gamma correction for displaying images, but with no clamping at 1. And so by testing a large variety of gamma values, that gave us our candidates. And so each pixel's error was only determined by that pixel itself, and it was just raising the pixel values to 1 over gamma.
Can you give more examples, more details on how you perform the importance sampling?
Yeah, so the sampling was according to pixel intensity. So a twice as bright pixel was twice as likely to be selected. And then obviously to make sure you didn't bias for Monte Carlo sampling, you have to adjust the errors according to those probabilities at the end. And it was really a simple algorithm of just sum up all the pixel values and create a PDF according to that. So it was just create an array of all the pixel values, create the cumulative distribution, and then take a random 1 to 0 and sample into there. And then nothing clever, like if it picked the same pixel twice, it just reran. So it was pretty brute force.
Okay, we'll do one more question. I'll try to get somewhat back on schedule, but given that the specific natural light used is such a large effect on the result, any thoughts on whether synthetic natural light could be created that optimizes for lower error across a range of materials?
I suspect that definitely could be done. And probably the important thing would be to make sure that your synthetic natural lighting was representative of, for lack of a better term, good natural lighting for judging material appearance. And so I suspect that you need a lot of samples of natural lighting to create a good sort of database of the statistics of natural lighting, and definitely something that future work should work on. But we were much more concerned with the BRDF side than the lighting side, and we're happy to just work with the best natural lighting that we found.
Okay, thank you. And thank you for a great presentation and for working through all the technical, and I thank you again.
No problem. Thank you very much.
So we'll go on to our second presentation, and this is with Surush Saryazdi, and we'll do the same thing. You'll be able to see the presenter live in the window, and then we'll have the recorded, and then we'll go to questions. Okay.
In this talk, we present the paper The Problem of Entangled Material Properties in SVBRDF Recovery. I'm Saryazdi, and this work is done in collaboration with Christian Murphy and Sudhir Mudur from the Computer Science Department at Concordia University. The appearance of an object depends on the view, light source, and the way in which light gets scattered by the surface and material of the object. For an opaque surface, this light interaction is modeled by a four-dimensional function called the bidirectional reflectance distribution function, or BRDF for short, which models the output light in any direction as a function of the incoming light in any direction. The BRDF is parameterized by four material properties: normal direction, which we denote by N, diffuse albedo, which we denote by D, specular roughness denoted by R, and specular albedo denoted by S. The SVBRDF, or the spatially varying BRDF, describes the BRDF over a 2D location over an object's surface. The SVBRDF properties consist of a 3-channel normal map to account for fine variations in surface geometry, a 3-channel RGB diffuse albedo map, a single-channel specular roughness for reflectiveness, and a 3-channel RGB specular albedo map. These parameters are represented per pixel in a 2D grid structure. We then input these material property maps along with light and view directions into our GGX rendering function to get a rendering of the material. In this paper, we focus on the problems encountered during SVBRDF recovery. SVBRDF recovery is concerned with deriving the material properties of an object from one or more images of the material. Doing so will enable us to re-render the material for other tasks, such as modeling the material in a video game environment, or using the recovered maps in downstream tasks, such as using them to classify the material type. Earlier work in this field focuses on recovering material properties from calibrated captures using dedicated acquisition setups. While these approaches can recover nice BRDFs, they require specialized hardware for image acquisition in addition to a large number of input images. For our purposes, we focus on methods of spatially varying BRDF recovery, which use casual captures of materials in the wild. This means that we do not have information about the light and view condition of the captures. This makes the problem highly underspecified and challenging, since an object can look quite different from different angles and with different light directions. While many solutions have been attempted for recovering SVBRDF properties under varying assumptions, the most promising solutions to date are those which use supervised deep learning techniques. Deep learning approaches tackle the underspecification problem by learning priors over the material property maps and the light and view directions used during training. Most successful deep learning architectures used in this area are encoder-decoder type architectures, which take a look at the entire image to get a better sense of the light and view conditions and the material type, and then proceed to make a prediction for the material property of each individual pixel. For the choice of our loss function for supervised training of the deep learning model, the first option that comes to mind is to use an L1 or L2 loss on the predicted material property maps compared to the ground truth maps. This was the loss function adopted by some of the earlier works in this domain. As an example of using the map loss for training the neural network, we can refer to Lee et al.'s work, which trains an encoder-decoder architecture using the map loss. However, we can see that even though the recovered material properties look reasonable qualitatively, the re-rendering of the material does not resemble the original material capture too well. The other option for a loss function is the rendering loss. The rendering loss is the L1 or L2 loss between renderings of ground truth and predicted material property maps under some light and view direction. The rendering loss was shown to be more effective and hence gets used in all recent work. Using this loss as opposed to the traditional L1 or L2 loss on predicted maps lets the physical meanings of each map and the interplay between them to be relegated to the update steps. Since the rendering loss is light and view dependent, in practice the average of the rendering loss over multiple randomly sampled light and view directions is used for training. We note that this is the Monte Carlo method for approximating the expectation of the rendering loss over different light and view directions. To demonstrate the effect of training with the rendering loss, Deschantre et al. Conducted an experiment of training the same model architecture 2 different times, once with the L1 map loss and another time with the rendering loss. The first row shows the ground truth material property maps and rendering of the material. The second row shows the SVBRDF predictions of the model trained with the L1 loss for a test input image. As can be seen, the rendering of the predictions does not accurately reproduce the appearance of the target material. On the last row, we have the SVBRDF predictions of the model trained using the rendering loss. While the predictions of this model are not necessarily identical in terms of the parameter values, they reproduce the ground truth rendered appearance well. As shown, training a model with the rendering loss provides the benefit of predicting material property maps that generate better renders. However, the rendering loss comes with several important drawbacks. Firstly, models trained with rendering loss tend to compensate for the incorrectness in one of the predicted maps by modifying another map in a way that would give a similar render. An example of this is shown in the bottom figure, where a model trained with rendering loss predicts a pinkish color as part of the specular map to compensate for the incorrect diffuse albedo map, yielding a rendering that closely resembles the ground truth rendering. Although the re-rendering of the predicted SVBRDF maps still looks good, we care about the correct prediction of individual maps as well, since accurate maps are essential when the BRDFs are used in various downstream applications. One example of this is to use the material properties to predict the material type, such as wood or metal. Another example is that for the use case of artists, we need material property maps that are easy to edit and modify by the artists, since each property map has a specific physical meaning associated to it. As another example, having accurate SVBRDF maps results in realistic objects when the material is inserted in mixed reality environments. One of the reasons for the entangled maps is that the rendering loss under limited light and view directions has multiple global minima. This is because 2 very different combinations of SVBRDF maps can generate the same rendering under limited light and view directions. To demonstrate this experimentally, we draw the contour plot of the rendering loss as a function of the predicted specular albedo and the predicted specular roughness. We set the predicted diffuse albedo and predicted normal map as constants equal to their ground truth values, so that we get a 2D contour plot of the loss. Ideally, the loss function should only have one global minimum where the predicted specular albedo and roughness values are equal to that of the ground truth. However, as can be seen, multiple global minima exist when using a single light and view sample, corresponding to different combinations of the specular albedo and specular roughness, which can yield the same rendering result. The ground truth value for the specular albedo and specular roughness corresponds to only one of these global minima points, as shown on the figure with an X. As a second drawback, the many-to-one nature of the rendering function implies that the gradient is either 0 or non-zero with respect to all 4 property maps. For example, if during training the network has already learned to predict 3 of the 4 maps correctly and has a mistake in one of them, which causes the render to look different, then the rendering loss will have non-zero gradients with respect to all 4 maps, thus making the network forget about maps it has already learned to correctly predict. Similarly, if during training the network finds a different combination of material properties that yields the same rendering while having incorrect individual maps, the rendering loss will have 0 gradients with respect to all 4 maps. As a third drawback, the number of light and view directions to be used in the rendering loss is a heuristic that needs to be selected empirically. As mentioned before, using a single light and view direction for render loss represents many loss minima possible, shown in the left side of below figure. However, as we increase light and view samples, the problem of multiple global minima is reduced, as shown in the right side of the figure where we use 100 light and view samples. Sampling more light and view directions would result in a more accurate approximation of the expectation of the rendering loss, albeit at the cost of more computation. Most recent works empirically used 9 renders to compute the loss, as they find it has the best computation to test render accuracy trade-off. For alleviating the aforementioned drawbacks, we make a few suggestions for future work. Firstly, to alleviate the problem of entangled property maps, one solution could be to simply parameterize the rendering function with only one of the predicted maps at a time, while using ground truth maps for the rest of the maps. With this change, the error of each map can correctly be backtraced to that map, while also considering the contribution of each map in the final rendering. This alleviates the problem of having multiple global minima by disabling other property maps from trying to compensate the shortcomings of one of the maps. This also alleviates the problem of harmful gradients. A second solution for reducing entanglement is by imposing priors on the predicted property maps. For example, we can have the model predict whether the input material is a dielectric or conductor, and if it is a conductor, then we immediately know that there is no diffuse component. Thirdly, one can look into adopting strategies used for disentanglement from other domains, such as learning of disentangled representations from video, and adopt those strategies in the field of SVBRDF recovery. As mentioned before, sampling different light and view directions for the rendering loss corresponds to the Monte Carlo method for approximating the expectation of the rendering loss. Thus, one can eliminate the dependence on a discrete number of views if one could find a closed-form solution for the expectation of the rendering loss over the light and view directions over the hemisphere. This double integral over light and view directions might be solvable with reasonable simplifications and approximations. For example, limiting the distribution of light and view directions to a subsample of the hemisphere, which would simplify the solution of the integral. Whether this integral can have a simple closed-form solution can be an interesting direction to look at for future work. Lastly, we might be able to address the network forgetfulness caused by the harmful gradients by applying a continual learning strategy and treating the learning of different material properties as a sequence of tasks. Thank you for your attention.
Thank you very much for a lovely presentation. And now we want to open it up for questions. Remember to go to Rocket and to the channel with the hashtag with the title, The Problem of Entanglement. I'd like to start off. I mean, this is a very basic problem we have, and we don't want to go to, having, 100 samples, because the whole point of a lot of this was to take things in just one image. Is one possible approach to have the sort of a small number of assumptions we can make and just have the networks give us like 4 possible solutions instead of saying like, oh, we have to be given one, this is the solution for this image, but could give us, 4 options of the possibilities, given that there's this ambiguity.
I think that's a very reasonable approach as well. Like we can, I think that can definitely also be looked into for future work if the network gives us multiple possible solutions. But maybe like as long as the solutions are not closely related to each other, like we don't want solutions that all kind of look the same in terms of the map predictions. But yeah, I think that can be good to look at for future works.
We have another question. Could you elaborate on your very last slide about lifelong learning?
So the problem with network forgetfulness was that, so since we have like harmful gradients, meaning that even if one of the maps is corrected, if 3 of the maps are predicted correctly and only one of them is predicted incorrectly, we're still gonna have gradients with respect to all 4 maps, which means that we're gonna unlearn some of the learning that we've already done. So like one of the propositions is that maybe through continual learning, we'll be able to keep learning new stuff as we get new training data, so that we can alleviate the forgetfulness of the network.
And some additional questions. Yeah, this is, I think, like I say, it's a big issue because we want to create nets to give us solutions to these ambiguous problems, but then you have the entanglement problem. I don't see other immediate questions, but thank you for your response. And I think because we are, running a little behind, I think we'll take this up again then in the general discussion, because it's a very fundamental problem here. And we'll thank you again. And we'll move to the third and final presentation in this session. And this is going to be on improving spectral upsampling with fluorescence. The authors are Lars König, Elisa Jung, and Karsten Dachsbacher. And Elisa's here as the presenter, and I'll turn it over to the recorded presentation.
Hello everyone, my name is Elisa, and I would like to tell you how we improved spectral upsampling with fluorescence. This work is based on last year's EGSR paper, Wide Gamut Spectral Upsampling with Fluorescence. So first I will recap what spectral upsampling is and how fluorescence can help it, and then I will tell you 3 ways in which we extended this approach. So to render colors and their interactions properly, we need to do spectral rendering, which means that we need to consider how light interacts with matter depending on its wavelength using reflectance spectra, because that is what we also have in the real world. However, most assets that we have today are given in RGB, which means that each color is represented by 3 discrete values instead of a continuous spectrum. So in order to do spectral rendering, we have to transform these RGB triples to reflectance spectra, which is called spectral upsampling. And a recent method for this was proposed by Jakob and Hanika, who modeled their reflectance spectra analytically as a polynomial, which is then mapped through a sigmoid squashing function. And this function makes sure that the resulting spectra are always bound between 0 and 1, which we need for physically valid spectra. And what's nice about this model is that each spectrum is parameterized by only 3 coefficients, which means that we can convert any RGB asset to a coefficient asset without actually having to store any more data. And this model can produce N-shaped and U-shaped spectra, more box-like spectra, or even constant ones. However, it turns out that the gamut of physically valid reflectances does not actually cover all visible colors, but only colors up to a certain brightness and saturation, and such extreme colors can only be represented by such extreme box-like spectra which aren't really realistic. So what last year's EGSR paper did was use the analytical reflectance model by Jakob and Hanika, and they achieved a wider gamut by adding fluorescence whenever the RGB color was too bright and saturated to be recreated by a physically valid reflectance spectrum bound between 0 and 1. And that works because fluorescent materials absorb light at one wavelength and then re-emit it at another longer wavelength, which is described by an absorption and emission spectrum. And this means that the apparent reflectivity of such a material can exceed 1 for some wavelengths while still being physically realistic. And last year's paper models the fluorescent absorption and emission spectrum based on B-splines and combines them with the reflectance model by Jakob and Hanika to achieve such apparent reflectances and more saturated colors. They need 1 parameter for the emission spectrum's peak wavelength, 1 for the width and distance between the 2 spectra, and 1 parameter for mixing fluorescence with reflectance, which controls the amount of fluorescence in the final spectrum. So, to convert an RGB triple to this model, we need to optimize 3 reflectance and 3 fluorescence coefficients to fit the model to some RGB color. And this is quite time-consuming, so we do this in a pre-computation step. And for that, the original paper divides the RGB color cube with a regular grid, and for each of the grid points, it optimizes and stores 6 coefficients by minimizing the Euclidean distance between the grid point and the RGB color that is represented by these coefficients. And in order to upsample colors between the grid points, they interpolate the coefficients that were pre-computed for those grid points. Now, we present 3 variations to this approach. First, we use another color difference metric during the optimization process. Then we replace the analytical fluorescence model with real-world measurements of fluorescent substances. And finally, we propose an alternative parameterization for the analytical reflectance spectra to help with interpolation. So let's start with the color difference metric. So as I mentioned before, the original paper optimizes coefficients by minimizing the Euclidean distance between a target color and the color that is represented by the current coefficients. And this is easy to implement and fast to compute, but while it does converge to zero if the colors get close enough, it does not accurately represent how we as humans perceive color differences. So instead, we use the delta E76 metric, which is defined as the Euclidean distance in the LAB color space, and the delta E2000 metric, which is based on the LCH color space and is a bit more complicated to compute. Next, I will show you some layers of pre-computed coefficients from a 32 by 32 by 32 regular grid in the ACCG AP1 color space. And the reason we chose this color space is that it is a wide gamut color space with quite extreme primaries, as you can see on the right, so it actually contains colors which are too saturated to be represented without fluorescence. So especially for fewer iterations, so for example 4, using the Euclidean distance in RGB as a color difference metric shows several artifacts. Using the delta E76 metric leads to a faster convergence, and the result appears more smooth to a human observer. And the remaining artifacts in the first layer disappear with more optimization iterations at the cost of a higher computation time and with some remaining artifacts, or when using the delta E2000 metrics at only 4 iterations and with only a slight computational overhead. Okay, so next let's take a closer look at the fluorescence model. So the analytical model from the previous paper is based on several simplifying assumptions about fluorescence and limits the shape of possible absorption and emission spectra. So for a more realistic model, we use measurements from real-world fluorescent substances. We selected 8 fluorescent materials with emission spectra all over the visible wavelength range and sorted them by their emission spectrum's chromaticity. And to achieve an even wider range of colors and smooth transitions, we interpolate pairs of adjacent substances before mixing the interpolated fluorescence with the analytical reflectance spectrum. So we also need to store 3 coefficients: the index of the interpolated pair, the interpolation weight, and, as in the analytical model, the mixing coefficient. And one thing that we need to note here is that the pair ID can only take on 8 discrete values. On the upside, this means that we only need 3 bits to store it, but on the downside, the optimization process is based on a continuous target function, so we can't simply ask the optimizer to fit our 3 coefficients. So instead, we perform a brute force search over all 8 pairs of adjacent measurements, and for each pair we run the optimizer for the remaining 5 coefficients to find the best fit. So because of the more complex optimization process, after only 4 optimization iterations, the database model still has significant artifacts, which simply means that there are entries where the optimizer has not yet found a close enough fit. And with 32 iterations, most of these artifacts disappear. However, some artifacts remain where the fit is still different from the target color, and some of those may actually disappear with even more iterations, because the optimizer also managed to find good fits for neighboring entries. However, some of these artifacts actually seem like they might be caused by some kind of transition issues where we transition between different types of fluorescent substances or spectrum shapes. And we have to admit that at the same iteration count, the analytical model does achieve a smoother solution. Now, if we look at the gamut of the coefficients in the pre-computed cube for the analytical and database model, we can see that the gamuts are more or less similar. The database gamut actually seems a bit larger at some corners, however the analytical gamut has a better resolution near center colors, but still they kind of cover the same shape, so this suggests that in principle it should be possible to represent all colors in the ACCG color space with the database model, and maybe for some entries the optimizer just hasn't found the corresponding coefficients. Finally, let's take a closer look at how the reflectance model behaves under interpolation. So if we have 2 colors that are represented by 2 analytical reflectance spectra, and we interpolate those 2 colors linearly, what we would like to get is something like this, which are the colors that are represented by the interpolated reflectance spectra. However, if we interpolate the reflectance coefficients instead before transforming them to a spectrum and transforming that to a color, the result looks like this. This is caused by the fact that the analytical reflectance model behaves non-linearly with linearly changing coefficients. But because the individual spectra themselves still have some nice properties, such as the smooth shape and being bound by 0 and 1, we still wanted to stick with the model but find a more intuitive parameterization with better interpolation properties. So instead of defining the reflectance directly with these three parameters C0, Z1 and C2, we define the spectrum in terms of the shift, which is the center of the spectrum, the width, which is the distance from the center to the point of the largest slope, and that largest slope itself, where we use the sign of the slope to represent U-shaped or N-shaped spectra. Now, you can already tell by looking at the coefficients what the corresponding spectrum looks like, and you can design spectra by hand much more easily. And we can convert these new parameters to the old parameters with this algorithm, which only requires elementary operations and a few square roots. So now, during the parameter fitting process, we optimize the new coefficients, transform those to the old coefficients, transform those to a spectrum, and transform that to a color. Now, if we go back to the example from before, the result of interpolating the coefficients is overall closer to the ground truth. However, this new parameterization also comes with some issues. The first one is modeling highly unsaturated, or in other words, gray colors. With the old model, such colors could be represented simply by setting the first two coefficients to 0 and using the last parameter to control the brightness of the resulting constant spectrum. Although, again, linearly changing C2 does not necessarily result in a linear change in the spectrum or its brightness. Now, with our new parameterization, defining gray spectra is actually a bit more complex, but we can still do it by keeping the shift constant and simultaneously increasing the width and inversely decreasing the slope. So, while we can't produce a perfectly constant spectrum, we can get extremely flat curves which basically result in the same gray color. However, in order to define such colors, we need quite extreme values, which can cause issues with the interpolation. The other issue is the slope value, because we use negative slope values for N-shaped spectra, as in this example, and positive slope values for U-shaped spectra. And in this example, the spectrum on the left has a slope value of minus 0.001, so really small. However, if we change the slope value to be plus 0.001, we get this jump. So when transitioning from negative to positive values, we get a discontinuity. Plus, for slope values of exactly 0, the resulting spectrum is actually not defined, since in the algorithm which transforms the new coefficients to the old ones, we need to divide by the slope. And this will cause artifacts when interpolating a U-shaped and an N-shaped spectrum. So in this example, we have two similar colors, but one is described by a U-shaped spectrum with a slope of 0.05, and the other is described by an N-shaped spectrum with a slope of minus 0.05. And if we interpolate the new coefficients, we get some really weird results, especially for interpolation weights that cause the interpolated slope value to get close to 0, because this gives us really flat spectra that jump when we transition from positive to negative values. And of course, this is an artificial example, and what's perhaps more interesting is what happens when we interpolate the pre-computed coefficients from the regular grid inside the RGB color cube. So for reference, these are the colors that are represented by the optimized new coefficients without any interpolation, and this is what we get when we linearly interpolate the new coefficients. And again, we can see these strong artifacts that correspond to the white to black jump whenever we transition from U-shaped to N-shaped spectra. And one approach which fixes this particular type of artifact is a hybrid interpolation approach, which combines interpolating the new coefficients with interpolating the old coefficients, where whenever we detect that the interpolation contains both U-shaped and N-shaped spectra, we first convert the new coefficients to the old coefficients and then interpolate the old coefficients. Now, both the new and the old interpolations still have some different types of artifacts, though we are not yet quite sure what causes them, But we can observe that they occur in different regions, so maybe it's possible to develop a more intelligent hybrid interpolation which kind of detects which of the two parameterizations is better suited for interpolation. And this brings me to the end of my talk. To conclude, we propose 3 variations to spectral upsampling with fluorescence. First, we used the delta E76 and delta E2000 color difference metric during the optimization process, and this was easy to implement and led to an overall faster and smoother convergence, so this is something I would definitely recommend. Second, we replaced the analytical fluorescence model with a data-based model, which offers a more realistic underlying model and achieves a similar gamut, but the discrete index of the interpolated data pair causes the optimization process to become much more complex and slower. And finally, we proposed alternative parameters for the analytical reflectance model, which are more intuitive but introduce different artifacts than before, which might be solved by a more intelligent hybrid interpolation approach, which we leave for future work. I hope you enjoyed this talk, and thank you so much for listening.
So thank you, Elisa, for the presentation. And we remind people to go to Rocket to the channel with the hashtag that has improving spectral upsampling to enter your questions. And good. So my first question is, I was interested in, can you describe to me the scenario where you're doing this interpolation, right? Is it for design, or when is it necessary to do this interpolation?
So the interpolation is necessary whenever you have an RGB asset. So for example, a texture or an image that you want to use as a texture, and you need to convert it to coefficients for rendering. So that's like the general scenario also without the fluorescence thing, right? Before you also had to do that you pre-compute coefficients for some RGB colors, but you can't compute them for all of them. Or maybe you want to and spend days pre-computing and have a huge lookup table, or you have a smaller lookup table, and then you have your texture, which has some RGB values, which are in between those grid points. So you have to interpolate coefficients for those colors.
I see. Yeah. And and this method is because the right answer is the in-between perceptual color, but you're saying that that's the interpolated spectrum is going to give you the interpolated perceptual color, or that is that assumption sort of implicit in this?
Okay, so I think one question here is, what does it mean to interpolate colors? Because if you do RGB rendering and you have colors interacting with each other, something like this, the result is not going to look like what you would get if you do spectral rendering and have spectra and interpolate those. So what does it even mean to have RGB colors and interpolate them? And we thought a reasonable thing to have as ground truth is to say, okay, we have those two spectra and we can look at the color that is represented by the spectra, and then we can interpolate the spectra and compare the resulting color with the color that we would get if we interpolate the coefficients and then transform the interpolated coefficients to a spectrum.
Okay, I should say, go to a question from the audience. For the interpolation issue, have you tried using some kind of optimal transport like Wasserstein distances?
Wait, let me look at the question. No, I've never heard of that. And we haven't tried it. No.
Yeah, I mean, well, I know, I mean, in data visualization, it's always a problem, like what the interpolated color is, because you interpolate in RGB red and blue, and you get something like magenta, and people think it should be the center of the rainbow because you're on opposite ends of the rainbow, so that you somehow should interpolate hue. So it's a difficult question. What does it mean to interpolate color? Make sure I'm not missing some more.
So one thing I can add to
here.
that is that So the example that I showed you with the blue and green is something that like highlights how the different models behave under interpolation. But what we have, if we pre-compute spectra for similar RGB colors, which is what we have in the grid, right? If we go from 0 red to 1 red in 32 steps, the difference between the colors is not going to be that big. So we're not going to interpolate between blue and red. We're more likely to interpolate between red and slightly less saturated red.
Okay, yeah, makes sense. Makes sense. Yeah, more of a just noticeable difference kind of stuff than radical changes. Okay. I'm not. Yeah, I think there's some also delay in people hearing the discussion and people entering the questions. Yes. So what kind of materials did you measure the fluorescence on?
We didn't measure the fluorescence ourselves. We went on the internet and downloaded measurements of fluorescent dyes. I don't remember all of them. I think some of them were actually fluorescent dyes that you can purchase for biotechnological things where you put dyes in the water to trace how the water flows. And they sell those dyes in all kinds of different colors. And what we would have wanted to do is use measurements for the dyes that are actually used in the industry. So for example, if you produce a fire truck for kids or something like that, there is some red fluorescent dye in there to make it super bright. But we couldn't find out which kind of dyes the toy producers used exactly. So we just used some dyes that were available online.
So once again, there's probably delay, but because to try to get somewhat back on track, we'll save additional questions for the final session. And thank you again very much for a lovely presentation and for doing this Q&A on the fly here. Thank you.
Thank you.